Welcome and welcome back to my channel. Today I want to discuss a question: if I want to introduce a new variable, how R squared would be changed? Would it be smaller or larger? And the question today is, if y is regressed on x1, R squared is 0.3, and if y is regressed on x2, R squared is 0.4. And what's the R squared if y is regressed on both x1 and x2? So before we go to the math and statistics part, I usually like to guess the results by intuition. I guess the R squared would be at least 0.4 because you at least have a variable x2 there, and if x1 and x2 correlation is perfectly like +1 or -1, which means that the introduction of x1 into the regression will not have any additional explaining power compared to the existing variable x2, and the upper bound of R squared, I guess, would be likely to be larger than 0.7, but I'm not sure whether it can reach up to 1. So let's take a deep look at it. So let's start from one variable. R squared is the correlation between y and x. So R squared, if there's only a single variable regression, the correlation between y and x. Alright, if we want to introduce a new variable like x1 and x2 into the R squared, we will have the matrix relationship like this. So the R squared will be likely to equal to, because R squared is only one number, so you can regard it as a 1 by 1 matrix. So the first matrix will be the correlation y between y and x1 and the correlation between 1 and x2. And this is a 1 by 1, 1 by 2 matrix. And times the inverse of the correlation matrix between x1 and x2. So correlation matrix, the diagonal elements should be equal to 1, and correlation between x1 and x2, correlation between x2 and x1, and you take the inverse. And the final correlation, final matrix will be 2 by 1 matrix, which is the correlation between x1 and y, x2 and y. Alright, so the final the correlation will be 1 by 1. Alright, so regarding take the inverse of the matrix, there's a tricky way to get inverse of the 2 by 2 matrix. So if we have the matrix of A, B, C, D, and if you take the inverse of that, it's just equal to, you take the opposite position between A and D. So here is D and here is A, and you put the negative sign before B and C. Alright, and then you times the reciprocal of the determinant. So it's 1 over A times D minus B times C. Alright, so by using this tricky way, it can help you a lot quickly solve the inverse of the 2 by 2 matrix, especially when you are in the interview. So the final answer will be R squared equal to 0.7 minus 0.4 times the square root of 3 times the rho. So I just simplify the rho here. The rho here means that the correlation between x1 and x2, I don't use the notation like this, I just use rho to simplify this equation, and then divided by 1 minus rho squared. Now the next question will be how this function looks like as a plot. You can use Wolfram to get a quick picture, or you can follow the traditional way to calculate the first order and the second order derivatives. And you make the first order derivatives equal to 1, and whether the second order derivatives are larger than 0 or smaller than 0 to know the local maximum and the local minimum. So here I do it in the easy way in the Python. So I plot the function like this one. So from the plots, the R squared goes down first to the points of 4, which is the same as we guess, and then goes up to 1. And you can see we can reach out to 1, up to 1 in 2 points. And the first point is that is around when the correlation between x1 and x2 is around negative 0.3. And the next one is when x1 and x2 are highly correlated. So when their correlation is around 0.99, it will be reached to 1. But be careful about a situation that between x1 and x2, situation is that the correlation, if the correlation between x1 and x2 equals to +1 or -1. So in these two cases, the correlation matrix is not invertible, so we cannot calculate R squared like in this way. And because x1 and x2 are perfectly linear correlated, either positive or negative, there is no additional explaining power, at least from a linear perspective. So let's wrap up here. So in this case, r squared can be very low, and the lowest r squared will be 0.4 up to the highest one equal to 1. And please note that the explaining power of r squared can be larger than the sum of the r squared that each variable regressed for the dependent variable y. So in this case, if one r squared is equal to 0.3, another one equal to 0.4, and the sum of them is equal to 0.7, the r squared can be larger than 0.7. Okay, that's all for today's topic, and thanks for watching it. If you like the video, please give me a thumb up and subscribe. I'll see you next week.